And then we will also try another a little bit more difficult example. Okay, here, as shown in this figure, here, many capacitors actually have a cylindrical shape. So let's try to calculate the capacitance of a cylindrical capacitor. So we consider the case that it has two cylinders inside the radius is A, and then the outside the radius is B. Of course, there is a gap between them, and then the length is L. And then let's assume that the inner surface, inner cylinder is charged with minus Q, and then the outer cylinder is charged by plus Q. Okay. Again, in this case, we will have to calculate using the Gauss law. So let's set up the Gaussian surface between these two plates with the radius r. Okay, and then you can see that everywhere on the Gaussian surface here, the electric field and then the area vector will be exactly opposite direction, and then electric field will be same everywhere here. Okay, and then we actually here do not bother to consider the this side or that side of the Gaussian surface because their electric flux will be 0. Okay, we're already familiar with it. Okay, and then let's try to calculate using the Gauss law. And in fact, how much charge is enclosed inside this Gauss law? It is in fact the total charge of the inner cylinder. It is in fact minus Q, but actually you can easily figure out here we don't really need a sign. So let's say the Q is the total charge enclosed, and that is equal to the epsilon naught multiplied by the electric field multiplied by the total surface area. Okay, and how much the total surface area is? Of course 2 pi r multiplied by the length of the cylinder. Okay, so here we can again rewrite now electric field is equal to Q divided by these other remaining things like epsilon naught 2 pi RL, right? So this is what we have to integrate in order to get the potential difference between these two plates. Okay, so here this is what we just got from the above equation, and all the rest are constant. Remember, all of them are constant, and only variable is here. Okay, so what is it if you integrate 1 over r with the r? Then remember from high school mathematics, if you have taken it, it is actually a natural log. If you integrate 1 over x with dx, then you will get a natural log of x. Okay, so here we have r, it's the same thing. So we are integrating natural log of r from a to b. So remember, natural log of b minus natural log of a can be written as natural log of b over a. Okay, this is what you get. And then finally, let's put back into the definition of the capacitor. So we need Q and delta V, which is already here, Q and delta V. So therefore, by summarizing it, this is the capacitance of the cylindrical capacitor. It certainly looks different from the capacitance of the parallel plate capacitor, right? Even though they look different, actually they have very similar properties. Why? In fact, this A represents the area of the capacitor, and then this L actually represents not exactly the area, but size of the capacitor. So if the L is long, we have effectively have a large area of the capacitor, so therefore it is effectively similar to having a large A. Okay, and then how about this part? If B is equal to A, that means these two plates are touching each other. It's just like D going to 0. So if these two plates are not exactly touching but very close to each other, then you will have a very large value of C. That is very similar to the case of having D very small. Okay, so these are very similar to each other. And then, well, please remember that regardless of the shape of the capacitor, the symbol is always the same. So we just saw the case of the cylindrical capacitor, but this is not a symbol. Yeah, we never draw a symbol like this. for any capacitor, symbol must be always like this, okay? And then, in the figure we have just seen, there were many capacitors together on the same board, right? So if you have many capacitors connected to each other, then how would this circuit behave? So as an example here, we have 3 capacitors actually connected to each other. And here on one side, one of these terminals are connected together. On the other side, the other terminals are also again connected together. We call this connection in parallel. So in this case, what will happen? These wires are all conductors. So therefore, if you connect this battery here, the electric potential will be all the same throughout this conductor, and again all the same throughout this conductor. So therefore, the potential difference across each capacitor become all the same. In this case, which is a V of the battery, okay? And then using the definition of the capacitance, we can say that for each capacitor, now we can write up C1 is equal to Q1 divided by V. Here the C1 will be the capacitance of the first capacitor, and Q1 will be the total charge accumulated inside this first capacitor. And then the second capacitor may have a different property. So C2 is equal to Q2 divided by V, which suggests that the amount of charge in the second capacitor may be different from that of the first capacitor. And again, for the third capacitor, it's the same. Okay, so here, remember that V are all the same, whereas C and Q may be different from each other. So therefore, we can use this. So that let's multiply V on each side of 3 equations. So for example, Q1 is equal to C1 multiplied by V. And then we can try to add these 3 equations multiplied by V. And then we can write up like this. So Q1 plus Q2 plus Q3, what is it? It is the total amount of charge accumulated in all of these 3 capacitors. So let's call this Q, okay? And then since V are all the same, we can now using the bracket, now C1 plus C2 plus C3 is multiplied by V, okay? In this equation, actually, where does Q come from? Q actually comes from the battery. Okay, battery is supplying Q and it is also supplying V, right? So therefore, we can actually think about it this way. Now, from the viewpoint of the battery, let's assume that this battery does not know how many capacitors there are. It only knows how much charge is supplying and how much electric potential is giving off. Then from the viewpoint of the battery, then we can think about how much charge is giving off and how much electric potential is applying. And then again, using the equation for the capacitance, now we can think about the actually how much effective capacitance is in this circuit is connected to the battery, okay? And then let's call it Q equi, which is an equivalent capacitor, okay? And then mathematically, if you take from the above equation, this equivalent capacitance is actually equal to C1 plus C2 plus C3. So what does it actually mean? So if there are many capacitors connected in parallel, just like shown in this figure, if you know the capacitance of each capacitor, then the total capacitance or equivalent capacitance experienced by any device outside them will be equal to the total linear summation of all the capacitance. So we can finally say if there are more than 3, even 100 or 1000, we can simply make a summation like this. This is the case of the capacitance when they are connected in parallel, okay? Okay, and then how about another example as shown in this figure? Now this time capacitors are connected one after another. So connection in this type is called the connection in series. Here you know that now V1, V2, V3, the electric potential across each capacitor may not be the same. Okay, and then can you see what other quantities may be the same between among capacitors? In fact, it's the charge. See that if you have a plus Q here, then of course there will be minus Q here. And then now the second capacitor is connected by the conducting wire. So therefore, if you have a minus Q going up, the plus Q has to go up because the total charge, the net charge initially has to be 0. And then finally, there will be minus Q again, and plus Q, and then again minus Q. So therefore, the amount of charge in each capacitor, in this case, become equal to each other. So therefore, you can now use the same definition of the capacitance and try to write down capacitance for each of the capacitor. Now see Q, Q, Q are the same, but V1, V2, V3 may not be the same. Okay, and then again see that here we cannot add charges against each other, but what other quantities can we add to each other? So here, actually, V1, V2, V3, if you add them together, that is actually equal to the total electric potential difference supplied by the battery. Okay, so therefore, let's do that. So you multiply V1, V2, V3 on each equation, and then try to add them. So this is the total electric potential, which is a summation between 3 electric potential. And then now you can write it this way, and then you can summarize this way. Okay, and then again we use the same trick. Again, let's say the battery does not know how many capacitors there are. It only knows that it's supplying Q and then also the electric potential V, and then it only thinks that there is some capacitor which stores charge Q, and then the electric potential V is applied. So why is total charge Q stored in this whole capacitor? Because on the whatever happens, on the top surface there will be plus Q, on the bottom surface there is minus Q. So as far as this battery is concerned, it has only supplied Q. Okay. So therefore, now let's call this capacitance as Q equivalent, and it will be convenient to write it in inverse form in this particular case. So 1 over C equivalent will be V divided by Q, is simply an inverse. And then take the equation from above, then you can write that it is actually equal to the summation of the inverse of each capacitance. Now it looks interesting, right? So if you have many of them, you can now say that instead of directly adding the capacitance, you have to add their inverse, and what you get will be the inverse capacitance. Okay, this is the this is how you combine different capacitance when these capacitors are connected in say in series. Okay. Okay, so far we learned that capacitors store electric charges, but in this slide we will learn that in fact capacitors store electric fields. Okay, now let me ask you a question. Suppose you try to charge a capacitor by increasing the amount of charge, and this process requires a work. Can you explain why? It is simply because of the Coulomb force. Take a look at the figure on the right side. Suppose now charge is increasing from say Q prime to Q prime plus dQ prime. Now the positive charge is moving from the negative plate to the positive plate. Okay, during this process, the charges that are already in the charged plate, say positive charges there, will be repelling additionally coming in positive charges. Okay, so therefore, because in order to overcome this Coulomb force, you have to do some work, and we will call it applied work. Okay, and then how is this applied work different from the work done by the Coulomb force that we have been discussing so far? Here we can write it this way. We have learned so far that the amount of work done by the Coulomb force is equal to the negative of the potential energy change, right? But in fact, the potential energy change is equal to the positive of the applied work outside, which means that think about that you try to lift something up. Then the change of the potential energy of this object when it's going up is equal to the amount of work you have to apply. Okay, that is how it is. And then now this change in potential energy can be calculated by multiplying the potential V prime by the change in this charge dq prime. Why? We have learned that the electric potential can be defined as the potential energy divided by the test charge, right? And in this process shown on the figure, this change in the charge, the moving charge dq prime, plays a role as a test charge. Okay, that is why. And then we also learned that now using the capacitance, V prime can be written as the Q prime divided by C. Okay, this comes from the definition of the capacitance. And then what we eventually want to calculate is the total amount of potential energy change, or the total amount of applied work while we are charging from 0 up to certain potential V. Okay, so we have to integrate this way. And then now let's insert in here. And then now we get the integration of the charge from 0 charge up to certain charge Q. Okay, and then we can express this integration using the graph here. So we are integrating the linear line, and then the slope of this line will be 1 over C. Okay, and then when we do integration, what we get is the area below the line. Okay, and then this will be the amount of applied work when the charge is up to Q prime. And then if the charge is changed by dq prime, then this is the additional work you have to supply, and that will go into the potential energy stored in the capacitor. Okay, and then finally we can perform the integration, and then we know that we always get 1 over 2 factor from the linear line integration, and then the total energy stored will be 1 over 2 CV square, or equivalently Q square divided by 2C. Okay, now we have learned that the electric charge is stored in a capacitor. It's actually the stored as a potential energy. And then how can you store large amount of potential energy? And of course, if we can build a large capacitor, then you can certainly store a large amount of charge and large amount of energy. But that is practically not very good. We always want to store large amount of energy in a small volume. So therefore, we introduce a useful concept, which is energy density, or energy per capacitor volume. And then how do we calculate this? Well, simply divide the electric energy by the capacitor volume. And then what is the volume of the parallel plate capacitor? Simply area multiplied by the distance between distance of the gap. Okay, the length of the gap, I mean. And then we just learned how to get the U. So this is something you get when you insert this. And then we also learned that the capacitance of the parallel plate capacitor is equal to E naught multiplied by A divided by D. So the A drops out here. Okay, and then you can summarize this way. And then what is this potential divided by the distance? It is the electric field. Okay, electric field here. So therefore, you can finally say that what is stored in the capacitor, if you consider it as an energy density, is in fact an electric field. Okay, this is why we say electric field is stored in the capacitor. Okay. Now let me throw you another question. What if we use for the integration, instead of using V prime dq prime, what if we use Q prime dV? Okay, the prime is missing here. What if we use Q prime dV prime? Okay, we will discuss the answer in the classroom. Okay.